Good morning and welcome to the Mars Base Camp Plenary. We're here live in Adelaide, Australia, and we're also streaming on Australia Science Channel. I'm super excited to be here and can't wait to see the presentation. I've got a few administrative tasks to accomplish first. We have volunteers in the audience, and the presentation we'll plan to leave time for questions. So if you raise your hand, I know the house lights are out, but raise your hand if you're here in the audience. A volunteer will find you, hand you a form, write down your question, and we'll try to get to as many of them as time permits after the presentation. Following the presentation for media, we'll have a press conference just out right around the corner. And then lastly, this presentation is not the end of the discussion about Mars exploration. So please bring us your comments and your ideas and your questions, Twitter, Facebook, or Instagram. If you want to share the live stream link, Twitter @Lockheed Martin or @RIAUS. By way of introductions, the presenters today are the architects and engineers who came up with the Mars Base Camp vision. To avoid the long introductions and get on with the show, suffice it to say they have as many degrees as my thermometer. But while I'm up here live streaming and live on stage, I'll take just a minute to tell you a few things about each of them that they might not share on their own.
You know we can hear you from the backstage, right?
Oh, okay. Well, they'll probably get over this. Once we get started, appearing on stage right, your left, will be Danielle Ritchie. A fun fact about Danielle is she is an Olympic power lifter and also a trained belly dancer. Appearing on stage left, your right, will be Tim Sheehan. Tim Sheehan is a bass guitar player in the band Beetlejuice, the brightest star in the constellation Orion, and also an avid stamp collector. Appearing center stage will be Rob Chambers, a man of many talents and skills. A couple of things: he built in his own basement a 600-gallon fish tank to house saltwater fish tank to house his personal pet, a moray eel, and also a quilter. And without further ado, let's hear the presentation on Mars Base Camp. Thank you.
We are explorers.
The time is now. At no other point in history have we had the technology, the know-how, and the public excitement to send humans past the moon and on to Mars.
We're building Orion now, a spacecraft like no other designed for deep space human exploration.
But to get to Mars, we can't just take Orion.
It needs to be part of a larger system that has the supplies and the scientific equipment required for a 1,000-day journey that will take us hundreds of millions of miles away.
We call our concept Mars Base Camp.
Last year, we presented an architecture on how to start exploring the Martian system by 2028. Mars Base Camp is a vision, one that requires international partnerships, collaboration with public and private institutions, as well as the technological know-how of everyone to achieve the greatest feat in human exploration history.
The U.S. Congress passed the NASA Transition Authorization Act of 2017 unanimously. Amongst all the other great things NASA does, it set forth plans to take humans to Mars in the 2030s and to set predecessor capabilities in cislunar space in the 2020s.
So NASA's looking for ideas. Now, one of the things that our bosses love is when we go off script to tell a little story, so we'll do that real quick before they cut our mics. So my wife, lovely wife, Michelle, and I have 3 kids. Middle kid is Evie, she's 11. And for the friends across the pond, she actually plays viola and rugby, which makes her a reasonably well-adjusted Yank, such as that goes. And we were driving in the car listening to the radio, and she said, "Daddy, that's a great song." This was a few years ago. She said, "Dad, that's a great song. Can you play it again?" And I said, "Well, no, it's the radio." And she's thinking that perhaps I was ignorant on how to operate the radio. She helpfully said, "Push a little left arrow." And I said, "That's not the rewind, that's a tuner." And she looked at me incredulously, and I said, "Look, it's like there's a guy out there with an iPod, and we're listening to it." And she's like, "Well, can we call him and ask him to play it?" And I said, "No, it's like everybody is listening everywhere to that same one iPod." And she looked at me like, "What are you?" And I said, "Look, turn off the radio. Let's just talk about how your day at school was today." So I tell that story for 2 reasons. First, for the space generation folks that are here, and for the millennials that might be watching on webcast. Someday you too will start getting old like Gen Xers and have to explain to the next generation the archaic aspects of your technology as you were growing up. But the other point, is that Mars Base Camp needs to be your playlist. You know, NASA's looking for ideas on how we're going to go out to the moon, how we go out to that deep space gateway, and then on to Mars. We've been exploring deep space for decades, and it's a team sport. It's probably the greatest team sport that's ever existed, with the exception of Australian rules football, as I've been finding out this week, but it's the second greatest team sport ever. It's bigger than a single country. It's something that all of humanity, need to do together. So as we talk through this today, this isn't Lockheed Martin's vision, and it's not the only vision of how to get to Mars. But we put it out here so that we can globally begin the dialogue and how to make it our playlist.
And to make it our playlist, at Lockheed Martin, we think you should actually look at your horizon goal of going to Mars, and then build your architecture for study and observation in cislunar space by really focusing on your horizon goal. So let's talk about how and why we can start exploring the Martian orbit, Martian system in about a decade.
So why? Why do we explore? Why do we hurl humans out into the solar system? At Lockheed Martin, it's always been about the science. There's fundamental questions that we've been asking for hundreds, if not thousands of years. Where did we come from? Where are we going? And are we alone in the cosmos? By sending human astronaut scientists to the Mars system, we're going to be gathering data and performing science that will help to answer these fundamental existential questions.
So using Mars Base Camp, we can take scientists on Earth and put them in Martian orbit. They can telerobotically operate rovers and UAVs, as well as explore the moons of Phobos and Deimos, as well as the Martian surface. In our reference architecture, we allocated 6,800 kilograms, or for those of you that like US units, 15,000 pounds, as well as 40,000 kilowatts of lab equipment and power to help the scientist astronauts make revolutionary discoveries with all of Earth's scientific community backing them up from home.
So Lockheed Martin's been a partner with NASA on every Mars mission in one role or another since Viking in 1976. And those orbiters and rovers have discovered amazing things about Mars, including that ancient Mars may have been able to support life. The Mars Reconnaissance Orbiter has shown that Mars is a complex, dynamic, evolving place. The Phoenix lander used its scoop and brushed off the dust and found that it was sitting on a large surface of water ice. The MAVEN spacecraft, and this is an illustration on the bottom left there, has shown that the solar wind is one of the reasons for Mars having lost its atmosphere. And the next spacecraft going to Mars, InSight, next year is going to study Mars's geologic evolution. So water is everywhere on Mars, frozen beneath the surface, and even liquid water flowing in special circumstances, as in the recurring slope Linné.
So Mars is dynamic. You know, when you look at a dynamic anything that you're studying, you need to be able to react to it. You need to be able to make real-time decisions as how to proceed based on what you've just learned or based on what is occurring in the thing that you're studying. And so putting astronauts into orbit around Mars allows us to react to these dynamic changing conditions that we never realized were there until the last decade or 15 years, running water on the surface of Mars.
Not only is Mars dynamic, it's big. Though it's smaller than our native planet, the surface area of Mars is equivalent to the entire landmass of Earth. So imagine trying to explore all of Earth's land with the several rovers. You can see here, this is a great example. Curiosity has been exploring Mars for 5 years. It's traveled 17 kilometers, or 10 miles in US units. And you can see when you zoom out and look at the entire Martian surface, we have so much more to explore.
So, you know, being able to drop those rovers, it's still a very large planet no matter what, but being able to react to what you see and drop rovers to these individual locations and with real-time control. You know, the light delay is what, 5 to 25 minutes from Earth to Mars. For Mars orbit, it's a quarter of a second. You can now safely and effectively drive those rovers from one area of interest to another faster than we've done in the past over the last 40 years.
And we don't need to invent new technologies or come up with some magical breakthrough. We have the capability to go to Mars now.
And that's an important point, and we're going to walk through the piece parts of the Mars Space Camp before we get into the new developments over the last year. But like Tony and I talked about last year, all of these elements are not new technology. All of these elements either exist in one form or another today or are actually in active development. So the physical center of Mars Base Camp is the center node with 2 cupolas. It need not be said that the cupolas came from ESA, right? They've been up on space station for almost a year. Many nations, including the Russians, have built a number of nodes which would serve the purpose, obviously, right here very well. Science, right? You need laboratory space to hold that 15,000 pounds, because I'm English, 15,000 pounds of lab equipment, 40 kilowatts of allocated power that Danielle talked about. Here we're showing labs and a living area that are made from a repurposed universal stage adapter from SLS. But many, many of our nations of our world have created, China, Japan, the Europeans, the Russians, and the Americans have created labs that have flown and are flying in space right now. We know how to do this.
So to give our astronauts something more exciting to do, we've added an excursion module. This is comprised of an airlock, which we've built and have existing here. We've used them on space station. And then something similar to a manned maneuvering unit. But this one, as you'll see in a few minutes, kind of has spider legs that allows our astronauts to explore the moons of Phobos and Deimos without disrupting all of the dirt that's on the surface, hopefully finding something like water ice. One of the key tenets of Mars Base Camp is self-rescue. This means that should something happen, should there be an emergency, our crew of 6 can find their way safely home. But to make the spacecraft more reliable, we have 2 of almost all the critical systems, starting off with our highly efficient, refuelable cryogenic propulsion stages, which you can see on the end, as well as the tank farms that hold the liquid oxygen and hydrogen.
And that self-rescue concept is really important. From the space station, you can be home in hours. From the moon, you can be home in days. But there isn't really abort options from Mars. Once you commit to that journey, you're on your own with your crew and your vehicle. And so we need to make sure that as we architect Mars systems, we can think of all the contingencies, and we can provide the crew with all the tools they need to solve any problem. Shown here is the solar electric propulsion cargo tug that's part of the Mars Base Camp concept. We use that tug to take the science lab and the center node out ahead of the astronauts. And the vehicle is reconfigured to have the astronauts go out in the transit configuration with all of the redundancy they need for the trip. And solar electric propulsion is really important and great for moving large pieces of cargo around, as well as in between each Mars Base Camp mission. The concept is to use the SEP tugs to reposition the science lab and the node there each time. And also to make sure that we are repurposing and using everything to the best we can, the solar arrays on the SEP tug then get repurposed for the main vehicle.
And of course, in that spirit of everything has to pull double duty, the solar electric propulsion, when you're done propelling, you have an enormous infrastructure, enormously powerful infrastructure, literally powerful. And that's what allows us to do this unprecedented science. But the heart and soul of Mars Base Camp is the Orion Command Deck and the associated deep space long-duration habitats that we're starting to build right now, and Tim's going to talk about that. Orion as the command deck, and yes, Orion should go to Mars. It's a 1,000-day vehicle. It was designed from the start for long-duration missions, and it needs supplies. It needs the living areas that we've talked about. But as the command and control deck, we can leverage the power distribution, the flight software, the avionics, the safety systems that are in place. It can serve as the command and control for the whole system, as well as a safe haven if anything goes wrong. It's critical and key to the safe exploration of the Mars system. And we've started, of course, already on Orion, and we've started on the habitats. Tim.
So Orion's first mission, Exploration Flight Test 1, was in 2014. I was in the engineering back room for that mission, and I remember that moment of liftoff, that first step into deep space. It's quite a moment. And we learned a lot from that flight and tested out all the systems. Now we've got Exploration Mission 1 down at Kennedy Space Center being built. That'll be an uncrewed flight around the moon in a high orbit over 25 days, further than any human-rated spacecraft has ever gone. And then the next mission, EM2, will be crewed and will take humans back to the moon for the first time since 1972. But the next step in cislunar space is really a gateway to the rest of the solar system. It's called the Deep Space Gateway. Here's our concept for it. And it's really a place to live and work in deep space, test out the technology, but maybe even important, test out the operations that we need to do in deep space, and perform great lunar science and exploration.
So I want to review just a little bit the architecture of Deep Space Gateway. We've talked about this a lot this week at IAC, and those of you who have been here may not have the privilege of sitting in on some of those fantastic sessions. So the Deep Space Gateway is comprised of several elements. At the very back end, you can see the power and propulsion element that says solar electric propulsion to move the Deep Space Gateway around cislunar space. In the center is the habitat where the astronauts work, hopefully eat, sleep, and exercise. At the top is an extravehicular activity module that allows astronauts to test out those procedures that they're going to need when they're at Mars, when they don't have Earth right next to them, backing them up, as we do at the space station, as well as to test out our advanced spacesuits. At the bottom is one of the components that really enables the Deep Space Gateway. That's a commercial logistics pod. International partners or commercial partners are critical to enabling us to explore cislunar space, and having them bring up supplies as well as additional equipment for us to test out is critical. You can see that there's a robotic arm. This looks really similar to what we have on the ISS. So again, we're using what we have today, what we know how to do. And this arm allows us to reconfigure the gateway as we get logistics pods or visiting vehicles. And like we talked about, Orion's here. Not only does it ferry the crew to the Earth, but initially, when we launch the Deep Space Gateway and assemble it in space, we leverage Orion and its systems while we develop the Deep Space Gateway habitat. In both Eclipse, the avionics, and again, we're looking at how do we support astronauts on their 1,000-day mission to Mars.
I'm guessing that everybody saw the announcement this morning that Russia has shown an interest in partnering with NASA on the Gateway, and that's great, right? We have two folks on the playlist. It's becoming an eclectic song mix, and that's fantastic, because this is the Gateway. This is the starting point that'll allow us to learn more about the moon and then move onward to Mars.
So one part of the Deep Space Gateway is the power and propulsion element. And it also has solar electric propulsion capability. And it is a prototype Mars SEP tug. And the technology there is really just a scaling up of what we fly today in geosynchronous orbit on our satellites, 12.5 kilowatt thrusters. And that's going to be, that efficiency, that high specific impulse is really going to be transformational for moving large pieces of cargo around the solar system. And for the Deep Space Gateway, we're going to also use it to move the whole gateway around different orbits around the moon. It's not a static vehicle. It's a vehicle that can travel around the lunar system.
What we're showing here is the extensibility of technology. Like Tim talked about, we have solar electric propulsion, and this is critical for exploration at the cislunar space as well as in Martian orbit. We're showing that you can take solar electric propulsion and scale up this element that we're using at the Deep Space Gateway, and pre-position elements like a laboratory, a center node and cupola, as well as a robotic arm, and any other type of technology you'd like to send out there in advance. One of the key enablers also for our exploration is enabling our commercial economy. Solar electric propulsion also allows our commercial partners to send out fuel for our refuelable systems. It's one of the critical technologies that really help us explore the entire solar system.
So solar electric propulsion in use now for well over a decade, and we're scaling it up today with the power and propulsion element that NASA is looking to build and start imminently. So what's another technology? What's another enabling technology that connects us with the DSG and then on to Mars Base Camp? Telerobotics. Time has shown us, arguably over the last 10 years, and then more with each passing year, robots and humans together can do so much more than they can independently. It's true synergism, right? And we talked earlier about the dynamic nature and having humans in orbit that can drop, hey, I'm going to drop a probe there and I'm going to send another probe there based on what I learned. And we can also transit quickly across that surface area, equal to the entire landmass of the Earth, like Danielle said. But there's another benefit of having the robotics and the humans in synergy, and that's tough terrain. Some of the most interesting places on both the moon and Mars are very hard to get to with standard rovers that like nice flat terrain.
So imagine you're in zero-G, Mars Base Camp, Deep Space Gateway, and you're operating a rover down on the surface, operating it through a lava tube, making decisions about where to go and what to examine, and really being able to accelerate the pace of science, and in some cases for the more mundane tasks like driving and just being able to go faster. And we understand that that'll take new classes of robots to explore these planets, but we're ready to take on that challenge.
So like Tim talked about, when you're operating UAVs, you can also telerobotically operate rovers from the Deep Space Gateway on the lunar surface. But one of the things I want to highlight is the international and commercial partners that are really driving innovation. Part-time scientists are a great example. They're offering up what they call the Audi Lunar Quattro. It's a robotic rover in which you can get a payload on it yourself and transmit data to a base. Now, one of the things the Deep Space Gateway offers is we could be a communication relay for your high bandwidth data that's being beamed from the lunar surface back to Earth.
So the key here is that partnership between humans and robots, handing off one to the other from autonomous to crew to different systems.
Actually, so Danielle and I had a chance to meet the part-time scientists folks in Beijing at GLEX this summer. And Danielle and them were talking nerdy engineering geek speak, and they said, oh, by the way, the rover talks to the lander that it comes in on via 3G wireless cell technology, effectively. So, of course, I leaned over and I said, oh, that means ET can actually phone home. And like half of them didn't get it. Which is another proof that the millennials are taking over without proper appreciation for cultural 1980s references.
I did get it.
So everything that we do with telerobotic systems is just going to accelerate our ability to cover large distances, the ability to respond to dynamic changing events, and the ability to go places that you can't go with humans or robots by themselves. But sometimes, like Grandma used to say, you got to get your hands on, right? Being able to go out to the moons of Phobos and Deimos, we alluded to earlier, Danielle talked about that excursion module and the spider legs here. And it's kind of like scuba diving, right? You don't want to stir up all the dust on these very low gravity bodies. And so you're walking along on these crawler legs, taking samples and testing them at Mars Base Camp, at the lab. But let's talk now about sample return, high value sample returns from both the moon and Mars.
So Mars Base Camp is a great staging point for receiving samples launched robotically from the surface of Mars. And in the beginning, we know how important those samples are, and there's planetary protection requirements, so we need to design all the facilities to do that. And the crew's role there will be to use their unique skills at rendezvous and docking, handling equipment in space, and to inspect and make sure the samples are still pristine, and so they can be placed on Orion to be sent home. But as we get more experience with those samples, the laboratory in orbit at Mars will, perhaps with the right precautions, be able to look at samples before sending them back. And of course, the Mars moon samples have less concern, and we'll be able to really curate those samples.
Safe, careful, high-integrity sampling and analysis is critical for understanding where we come from and how we fit into this world, as well as where are we going. It also allows for commercial markets to map those high-value resources on the lunar surface and really develop that commercial economy that will make our space exploration go that much further.
So all of these things, all of these capabilities, the processes, the ability to gather samples and to launch them, orbital rendezvous to grab them, the curation that Tim talked about. Those are all directly the things that we're going to do both at the moon and Mars for reasons at both locations.
So water is everywhere in the solar system, and anywhere we want to send humans, water is there. It really is the fuel for exploration, and not just for making hydrogen and oxygen rocket fuel, but also for the astronauts to drink and to create oxygen for them to breathe.
So in 2016, United Launch Alliance announced a study in which they put the price point of liquid oxygen and liquid hydrogen around cislunar space at $1,000 per kilogram and on the lunar surface of $500 per kilogram. Well, this is just an initial study, and it starts that conversation of how do we actually mine the materials, how do we enable our refuelable systems, and what can we do feeding forward to the Martian orbit?
So why did United Launch Alliance come out with this? Water-based economy. So one of the key tenets of Mars Base Camp that we talked about is those cryopropulsion stages, and they're LOX hydrogen, not methane, LOX hydrogen. A lot of folks have pointed out liquid hydrogen is cold, and it is. It's a mechanical engineering problem, and we actually have some ideas and that we're going to be sharing very soon on just how to keep that cold. It needs to be zero boil off. Use active cooling. The gear ratio, the efficiency, we measure it in pounds of force per pound of fuel consumed, is like 33% higher for hydrogen than it is for methane. And that is fundamental in allowing us to do some things. We're going to talk a little bit more about those this morning. But it also means we can create that fuel. We can power this entire spacecraft system just with water. No carbon feedstock, no other complex chemical equations. It's electrolysis. That is a water-based economy. And when you talk about the water-based economy, the commercial value of starting to do resources at the moon, we talk a lot about everything from helium-3 to raw minerals. You need to find something that Earthlings will buy. And it seems crazy, but Earthlings will buy water from the moon. Not to bring down to here and to drink. We have that water. To bring it to low Earth orbit and use it to service spacecraft and move things up to higher orbit. And that allows the commercial entities to tie into the LEO market, right? So that's the value creation. It's just one of many examples, but that's the water-based economy of the future. And that's what we've harnessed here with LOX hydrogen.
And we think that's very much key for exploration. Some of the new concepts this year is this water delivery vehicle, and the idea is to have that vehicle bring water to your orbiting base camp and use the large solar arrays to generate the hydrogen and oxygen propellant. And we see this as a great place for commercial entities to participate in deep space exploration. And we don't really care where the water comes from. Come from Earth. We know there's water on Earth, but it could come from asteroids. It could come from shadowed lunar polar craters. If we're really lucky, there's water on the Mars moons. It doesn't matter where that feedstock is. And we also know that there's a number of companies out there, entrepreneurial companies like Planetary Resources, who are working on this today. And we're really excited about that vision of water enabling deep space exploration.
So, telerobotics and solar electric propulsion, deep space restartable cryo, LOX hydrogen. These are all enablers for Mars Base Camp that allow us to do Mars Base Camp in about a decade, but it doesn't end in Mars orbit. Base camps are not a destination unto themselves. They're the place from which you then set out, in this case, to descend to the surfaces of other worlds.
That synergistic relationship between water-based economy And the highly efficient liquid oxygen, liquid hydrogen propulsive system allows us to take a new look and an approach at a lander, one that's refuelable, restartable, single stage. It's capable of landing on the Martian surface, supporting 4 astronauts for 2 weeks while they achieve unprecedented science objectives, and then returning back to Mars Base Camp without being dependent on any surface propellant generation.
So I'll go through a couple of facts and figures. The lander has 80 metric tons of propellant, about 30 metric ton dry mass, and it's the propulsion section is very much based upon the Mars Base Camp cryopropulsion stage. It has about 132,000 pounds of thrust. The crew cabin is based on Orion. Orion is a great deep space sortie vehicle. So all of those systems, life support, crew displays, avionics, those are all the systems that are in this lander. And from a delta V capability point of view, we've got about 6 kilometers per second of delta V capability. When we're re-entering, about 80% of that delta V for re-entry is done by aerodynamic drag, and then that 6 kilometers per second is used for the supersonic retropropulsion, and then for ascent back up to the surface.
So you're thinking, Lockheed Martin, this just looks like Jules Verne, and where are the big heat shields? And the answer is, you're starting from a base camp. You're starting from orbit. So when you look at the rovers and the landers that we've been working with NASA on for decades, right? We've been on Mars since 1976 with Viking. Those were direct entry systems. So they come straight from Earth to Mars, and they enter at a very high velocity, very large energy that you have to get out. So we use a combinations of heat shields and parachutes, and went from airbags to the sky crane that you saw with Curiosity. When you start from orbit around Mars, you're starting with like 5 kilometers per second. And for those that were scribbling really quickly, so 5 kilometers per second, you subtract off 80%, or 4 kilometers per second. For aerodynamic, use 1 kilometer per second of your delta V. And if you remember, we've got 6 kilometers per second of delta V with this vehicle, enabled by liquid hydrogen. Design doesn't close with methane, but it closes with liquid hydrogen. So it leaves you 5 kilometers per second for getting back out and getting to Mars Base Camp, and then going to where those water tenders are bringing you in. 5 kilometers per second sounds like a lot, but the atmosphere of Mars is thin. The entry, descent, and landing guys at JPL and at Denver say that the Mars atmosphere is enough to be annoying, but not enough to be really useful. And that's why we, when we're coming down after the parachutes, we have to do something else. Airbags, sky crane, or what have you. But this is to our advantage here. It's thin. So even coming in at 5 kilometers per second, the dynamic pressure, the forces on the airframe are on the order of what we saw with the SR-71 that Lockheed built and started flying 50 years ago. The heat, the integrated or the instantaneous heat, obviously very hot, right, on the nose cones and on the fins. So they have to be carbon reinforced, but it didn't have to be ablative. The heating isn't that high, so they're totally reusable. And then the titanium sides, titanium alloy, completely reusable. The integrated heat load for this thing is really less than you would get from a supersonic aircraft that has to fly for hours on end, because we're coming in and taking it quickly. So the integrated heat load really isn't as hard as the problems that we've had to solve even decades ago.
Upon returning to Mars Base Camp, the lander refuels from cracked water and then is ready for another Martian sortie. Imagine in the early days of Martian exploration, you can go anywhere on the Martian surface. This is a huge enabler from cost, complexity, and safety, which is extremely important.
And also, it reminds me of something we forgot to add, which is anytime abort capability. So one of the advantages of the lander is, as you're coming in, if you see something you don't like, you just pull out, right? Because you were going to do that 2 weeks later anyway and lift off directly from the surface. So that gives you the ability to then refuel in orbit and then give it another shot when you like what you see. Mission success and safety with an anytime abort with a single stage vehicle like this.
And with that access to the Mars surface, from a science perspective, being able to go to multiple locations with crew and then confirm your final landing location, that's great too. And so, extensibility and always knowing what's the next step, how does this fit in, that's a theme here as we go from Orion all the way forward. And so when we get to longer term operations on the surface of the moon, the idea here is that this is the crew transportation vehicle, and then for the larger pieces of cargo, there would be a one-way cargo lander. And also from a ISRU perspective, of course, there's lots of water on Mars. But what about the moon? The moon has got about half the gravity of Mars. It doesn't have an atmosphere. And when we've looked at the delta V that's required to go back and forth from the Deep Space Gateway or the lunar base camp, that's about 5 kilometers per second. So that's within the capability of this vehicle.
With the zero boil-off powered fuel system, the lander is extremely happy in the darkest craters on the lunar surface, exploring and getting valuable science from the South Pole Aitken Basin. The key to the lander into Mars Base Camp is really that thought of extensibility. We're using the technologies we have today, and with the lander, as an example, using the technologies like Orion that we're building today for tomorrow. Remember, the path to Mars is through cislunar space.
So I want to leave you with an image. And I'd ask you to just close your eyes just for a second. Since I totally can't see you anyway, I don't know if you do or not, but I've got my eyes closed. Imagine yourself in the Mars Base Camp, deep space transport, in between Earth and Mars, so maybe 3 or 4 months out. Earth has shrunk to just a pale blue dot, and Mars is still just a red pinprick in the sky. And the sun has gotten steadily smaller and dimmer as you've moved out. It's a colorless world out there, the magnificent desolation, to quote a famous person. But inside, you are surrounded with 5 people that look like none of us because they look like all of us, right? These are going to be the 6 people the most brave, adaptable, probably humble, able to work with others, finest folks that have ever walked this planet or any world in our solar system. And they're going to be, of all nationalities, they're going to be a swath of genders and backgrounds, experience bases. We're going to have engineers and technicians and doctors and psychiatrists and plumbers, electricians, 3D printer people. Those are the people that you're going to be sharing this experience with. And so for 9 months, there's magnificent desolation on the outside and your crew on the inside. And at that point, about 9 months in, everyone's going to flock to the windows because even the sun has gone away because you swung around the backside of Mars and you're doing your orbit insertion burn. And that's when the transformational event is going to occur. Sunrise over another planet, streaming in through the windows of Orion that the Americans contribute, and lighting up the interior of nodes and airlocks that perhaps the Russians contribute, and streaming in through lab windows, Chinese and Japanese perhaps, cupolas from ESA, lighting up the inside of a living area contributed by the Australian Space Agency. That is a transformational event for our generation. It's literally dawn of a new age of discovery about ourselves and about our solar system and our place in it. Ladies and gentlemen, we are all explorers, and the time is now.
All right, please welcome back to the stage Danielle, Tim, and Rob, please. Thank you very much. I got a few questions submitted from the audience, but not very many, and we might have time for more, and they're coming up right now. So raise your hand up high if you need a piece of paper to submit a question. I got a couple for the audience real quick. Who wants to fly on Orion?
Oh, audience, sorry.
Who wants to fly on Orion to cislunar space and live and work on the Deep Space Gateway? Pretty good. Everybody's up for these questions. There's harder ones coming. Who wants to leave Earth on Orion, spend some time getting ready in the Deep Space Gateway, and then climb aboard Mars Base Camp, take the round trip, long voyage to Mars and back to Earth? All right, that's the end of the easy ones. Guess what? There's only 4 folks that get to fly and work on the Deep Space Gateway initially. And then, as Rob said, only about 6 on the first trip of Mars Base Camp till we get this up and going and establish a regular cadence. Who's willing to stay on Earth and dedicate their energy and their efforts and their treasure to make this a reality for all of humankind? All right, I picked the right audience. Okay, now for the 3 of you, some of these questions are pretty hard. Rob, I think you covered this right at the end. Is there a role for the Australian Space Agency to play?
Yes. Actually, first role is Canberra, right? So Deep Space Network, there are 3 sites across the world. Australia is one. For any of you, who has seen the movie The Dish? Who has seen E.T., by the way? All right. Thank God. So The Dish, fantastic movie, and actually very, very cool. And it's about Australia's role when we landed on the moon. Canberra is an important part. It covers like 120 degrees of, you can calculate the steradians from that, Mr. Jihan. It's critical for deep space communications, which will include Orion as we start to go out both to the moon and then on to Mars. But that's the easy part, because that exists today. Every one of our systems has components that will be coming from across the world. So pick your favorite thing. Pick what you're good at, like Grandma used to say, and go after that.
Excellent, thank you. All right, these next ones, I'm going to combine a couple, and it basically comes down to LOX. So we're going to talk rocket liquid engine propulsion. LOX hydrogen versus methane. Tim, this is probably yours, and it comes in a couple of flavors. It's essentially why LOX hydrogen and not methane? Is there benefit to having both? And it's also a separate question about transfer of liquid hydrogen at microgravity.
Okay.
So why LOX hydrogen?
So a couple different reasons for the LOX hydrogen. Of course, the high efficiency is really important and enables things like the lander. We've also been working with hydrogen upper stages for a long time, including the Atlas Centaur all the way back to the 60s. So we know how to do those types of systems. To the question of should we have both hydrogen and methane? I think yes, that diversity of supply is important. But what we see is that making methane on the surface of Mars, that's definitely an application. But the water is in so many places in the solar system, so we want to have that diversity of supply chain of where your propellant feedstock is coming from. And then the last one was transfer of cryogenic fluids, and I assume storage of cryogenic fluids. There's nothing magical in the physics there. We've got some engineering to do, but even more than the engineering, we've got lots of ground tests that are working on that right now today at places like NASA Marshall. But it's time to start flying those cryogenic storage and transfer systems, demonstrating that technology. Maybe the Deep Space Gateway is a good place to do that, or do it in low Earth orbit.
Okay, one more propulsion question, Tim. What's the propellant for the solar electric propulsion?
Xenon.
Okay, there's a series of essentially what I'll refer to as crew health questions. So we'll split these up. There's a question about crew physical fitness, physical health, mental health, and then a radiation protection question. So
Yeah.
Dibs on radiation.
oh,
And then anti-dibs on the other ones.
that was the one I wanted because we've done so much work in that area. But okay, let's start with the radiation protection.
So there's two kinds of radiation you have to worry about, and a lot of you probably already know this. Galactic cosmic rays, hard to shield. We actually get a fair amount of benefit from hydrogen in those tanks. We tuck in the next step habitats that we've been talking about, the Deep Space Gateway. Those are the tanks within the tanks. Those are hidden there. So that gives us some benefit. But NASA and the medical offices have been looking and evaluating the galactic cosmic ray radiation impacts, relative to radiation workers here on Earth. And it looks like we're going to be okay there with some prudent type of shielding, like we just talked about. What you have to worry about, though, is solar events and solar particles. The issue there is that the background is okay, but then we have these solar particle events. And so on Orion, we actually have a couple of different things we're doing. One is what's called almost a safe box. It's made out of kind of a polyethylene type box you put together. We call it a storm shelter in case there's a solar storm. And I'm not sure about you guys, but if I had to go into a cozy, small 1 meter cube box with Antonelli for 2 weeks straight, there might be a better solution out there. And there is, no offense, but there is, fortunately, in the form of the next kind of step in that is the STEMRAD vests. And so if you get a chance, come over to the Lockheed booth and check that out. These are a joint activity with Israel and DLR for a personal protection device for those solar. See, you got me thinking solar electric.
Storms.
Thank you.
So I don't really want to talk about the crew health of Rob and Tony being in a box for 9 months, but I will start talking about crew health is one of the most important things when you talk about human exploration, especially on like a 1,000-day mission. So a couple parts, there's the physical and then there's the mental part. Physical, we seem to have a better understanding of that, though we're still working on it. That's one of the things that we're doing with the Deep Space Gateway, and NASA's really looking at is what equipment do we need, and then how do we make that equipment more compact? I don't know, have anybody heard of the Martian? It seems to be a pretty amazing, expansive space. The crew's not going to have that much room, and so we're really looking at, with using the Deep Space Gateway, how do we take the critical equipment in order to keep their bone density up, keep the muscle atrophy down, and really make sure that they're physically fit once they reach the Martian orbit, and especially Martian surface, to handle the loads of working and exploring there. As far as crew mental health, aside from these two, we do a lot of experiments here on Earth. I'd like to give a shout out. Josh Ehrlich just came out of 8 months in high seas. And so these analog research stations do a really good job of looking at crew interaction, making sure we don't have, an angry crew by the time they need to actually perform their work and their duties at Mars, and then how we're going to get them home. So I think those analogs are really critical to evaluating crew psychology, and then also the support here on Earth. It's, how do we make sure that the crew has time to themselves, has communication from their loved ones, as well as, has the stamina to make it through that 1,000-day mission and still be really upbeat and excited about what they do every day.
And everything's tied together. So as we design our vehicles, we need to take that all into account. And as an example, the crew exercise periods at the Deep Space Gateway are driving our systems. The heat and humidity generated by that, we've got to take into account.
Excellent. And then I'm not sure if you heard Misha Kornienko at last year's IAC, right after his 1-year mission. He talked about the day after his land and being in the gym. And then the one piece that I remember was swimming a kilometer right after his 1-year mission. So we're making great strides. We need to continue to study it and work it. I'm getting the hook. I got time for one more question. I guess maybe all three of you can take a shot at it. I want to remind the media right after this event, Danielle, Tim, and Rob will be available in the panorama room to answer more questions and conduct a press conference. And I didn't get through everybody's questions, but I really appreciate the feedback. We'll be in and around the Lockheed Martin booth if you want your question answered. So our final question, given the available time, if you're not in a national space agency, is there a role to play? Can you participate in the plan if you're not part of a national space agency? I guess I should remind you the four of us aren't in a national space agency.
I was just at Space Generation Conference last week at Congress, so call out to them. And every single person in that room can participate in space exploration. It's not only the people that are wearing the suits with the flags on their shoulders as astronauts, it's the people that are actually contributing the ideas, those brilliant revolutionary technologies that we need, as well as actually building the spacecrafts. They're going to take astronauts from today, like this image, to the Martian surface in Orion, as well as those that are going to help us revolutionize the power production plants and the commercial services to really going and taking our humanity into deep space.
Excellent. Okay, time is short. Please, one more round of applause for Danielle, Tim, and Rob.
Thank you.